Today we'll be playing with one of the most popular algorithms for character animation in video game. Hi, I'm Jerome, and today we'll be looking at motion matching for character animation. It's not a paper per se because it was never published as a paper, but it has been shown in a lot of different talks and GDC talks and stuff. And so the first thing that is important in motion matching is that you will have the future trajectory. You need to predict what your trajectory is, and only when you have your prediction, what you could do is try to find animations to dress that prediction. So you need to have a stable prediction. You need to know in advance what your character would need to be able to do. So for this, what I will do, in my case, I will work with the locomotion only as the first example, and I will use a spring damper model to compute how I want the character to move, and also compute at the same time the futures of where the character would be depending on those. I really recommend you to read the article from Daniel Holden that explain all the mathematics for the spring dampers, the critical spring damper, and how you could use that for a lot of different stuff. But in this case, to compute the position of a character, the velocity and acceleration, and predict where you want to use it. So really what I have is these functions, and that this one is the most important one. You give him a position at time 0, velocity at time 0, acceleration at time 0, a velocity goal, your half life, so it's how much time it takes for the spring to do half of the distance, and a delta time, and it will return the next position, next velocity, and next acceleration at that time. And that's a second order differential equation that has been solved. So the answer is correct. No matter what is the delta time you give him, any time in the future, it would actually have the exact position, velocity, and acceleration you will have in that time. So that's really powerful for that. So I get my gamepad, and I can, well, I have a little function to create a sphere I can draw. Then I get these functions. Basically, I'm computing the direction I want to move, the velocity I want to have, and the orientations I want to get. And you have this. So if I play this, now I can take my pad, and then I can, so the black is the current positions where I want to my character to be, and the yellows are the predicted position orientations I will have 10 frames in the future, 20 frames in the future, 30 frames in the future, so 1 second in the future there. So basically, and that's perfect. I mean, if I release, you could see that everyone stops on the same spots. So the prediction is perfect, and you can play with the half time to get something smoother if you need to, or if you want something faster in the interaction. And I've separate this in position, and the same for orientation. I can choose how quickly the orientation change and that kind of stuff. So that is one of the key need for the motion matching. You need to make sure that you have something that moves in a physically plausible way, and that's allow you to predict where you will be. In this case, you know, it's using spring damper to simulate the accelerations and velocities and all kind of stuff you could have. It could be any other system if you have something that works for you, but accurately predict where, accurately predict your trajectory. That's really what is important here. Now that I have this, I can actually load my character. I can load a little displacement. I can load a bunch of animations. So I will have all the running animation from the LAFAN database, and we could see the animations we have here. So basically, it's the character running in all directions, stopping, accelerating, going strafing animations. So I get several animations. I get a bunch of motion. Now, second thing that is important when you do motion matching, of course, we have our prediction of trajectory. We see that we've used velocities and acceleration, that kind of stuff. So we have something that is extremely smooth in the trajectory we generate. And we will want to match animation on those smooth trajectory. But my animation in this case, you could see that the root of my character is the projected hips on the ground and orientation. So that is a signal that oscillates a lot, and basically it's a signal that has a lot of small noises. And if I try to match the two, my data will not be perfect. I mean, I will have something that have a lot of noise, and I will try to match that noise. So what we need to do is to make sure that we remove the noise we have in the signal coming from the animation itself. And for this, I would use a filter that I will not try to pronounce, but because I will probably butcher the name badly, but I will use an SG filter, let's say. And what the filter does, if you have a signal that has a lot of noise into it, you will make a window, and you will try to you will slide that window slowly to compute the values. And every time inside of that window, you will match a polynomial of degree you choose. But you will basically fit a polynomial, take the middle value, move forward, fit the polynomial, take the middle value, move forward, fit the polynomial, and so on and so on. What I would do in my case for this motion, I would basically fit a window of 2 seconds, and I will fit a polynomial of degree 4 in the middle of the time for the positions, and I will go a little further and go 65 frames for the rotations, but fitting a polynomial of degree 5. So that's how I will smooth the signal. Now I will do this inside of a function that I called prepare data, because what you do usually when you have motion matching, that kind of stuff, that you would take all your animations and you would put that inside of what we call a database. That will be a flat structures of all your frame of animations. And so that's what this function does. It takes an animation, so the quaternions and positions of all the bones and transition and roots and that stuff. And I will smooth the signal. I will realign my animation to the smooth one. So the smooth root becomes the root of my animation. And then I will compute the velocities, the local velocities of all of my bones, and the local angular velocities of all of my bones. That would be useful for later at the end, but at least I have everything in my database. And so it returns, the animation, the quaternion, and the animation of the quaternions, the positions, the velocities, angular velocities. And then I get the frame range and the frame count. That will actually allows me to know in my database what are the range of each of an animations, because I will have all my animations back to back inside of my database, and my frame range will tell me well, that was an animation, that was one animation, that was one animation. And I will build that database for several animations and several ranges of animations, and I will have one big. So basically, this becomes that database. I get all my animations for everything. So if I display now this, so really displaying my database, I get this. You can see now that the displacement linked to the character is now smooth in orientations and positions. I don't have the little oscillation anymore. And now that we have our database of animation itself, we could start to think about how we will use that database to play animations. So how we will match the frames of animations to our future trajectories the way we want it. And for this, what we will do is that we will build a feature vector. So we will extract a bunch of features that we are interested in. And in the case of the locomotions, what will be the most interesting stuff for us will be the hips velocity. So how is the hips moving? I'll get the feet position and velocities. So I will know where my feet are and how they were moving. And then I will get the future states, which is sampled at 10, 20, 30 frames in the future inside of my animation. And I will sample the position of the character and the orientation of the character. So it's really the hips, the feet, velocity of the feet, and then the character positions and the character orientations. So that's how I will build my feature vector. And that's what I will do here. So basically what I'm doing is that I'm converting all my animations in global space. So I will be able to compute the position and velocity of my foot and my hips also. And then I will take my current frame. So I do it for every frame. So I take my first frame and I take the positions of frame +1, +10, +20, +30, just making sure that I'm actually never going over boundaries. So, you know, I had several animations back to back. I don't want to take future positions that comes from a different animation. I want to have future positions that only belongs to my current animation. And once you have all of those, what you do is that you bring back all the data as local to the current frame. So I computed I have my frame that is frame 0 is somewhere here in the world. I get the futures positions there, and I take all those positions and I bring them back into 0, 0, 0 relative to the current frame I'm computing. And when you have that, you could start to build your feature vector, and that will be a big flat features. You know, when I will have the velocity of my hips, the position of my left foot, position of my right foot, velocity of the feet, and then the future positions and the future orientations. And I do that for every frame. So it's the features becomes a tensor of size number of frames, and number of columns is 33 in my case here. It's all the 3D points and velocities I have. And then when I've computed all of these, we could start to display what it looks like. So this is what is extracted from our animation. So what we have is the local informations compared to all the current frames of where the foot positions are, the foot velocities, the hips velocity, and the future positions and orientations of the character. And we have that for every frame inside of our database. And that's basically it. I mean, I've extracted all of data. You know, I've already computed the future trajectory, so we will start to be able to match the future trajectory with the data we have here. The only issue we have right now is that all of this data has a lot of different values and sizes. You know, all the values that are from these points are fairly close around here, but the one is really far in the futures have big values. And what I have is one feature vector that is basically a vector in 33 dimensions. And I just want to be able to compute the Euclidean distance when I will be searching for the most similar pose. I will just do a flat Euclidean distance, but something will have a lot more importance than other. And I don't want to have to deal with this because it will be tricky to remember, maybe this one has a bigger value, this one has less value. I need to give more importance to this or to that. So what I would do is that I will normalize my vector. It's something that you always do when you do machine learnings and all of those stuff. That is, you normalize all of your values inside of your features. And to normalize them, basically, you take the average, the mean of all your values, you subtract the mean. So all your values, if they were all from 0 to 20, then you will switch, you will slide your window to be around 0. And then you divide all the values by the standard deviations. So the goal is to have, for all of your feature, to have a mean of 0 and a standard deviation of 1. So basically everything now is in same space. Everything has the same importance. And when you try to do an Euclidean distance on a flat vector like this, it would work. So this is what you do. You take the feature mean, the feature standard deviations. I need to add a really small error here because I have a bunch of values that are zeros everywhere because I've kept the y position of my trajectories. They're all zeros. So I keep the feature mean, feature standard deviation. So you take the features, remove the mean, divide by the standard deviations, and that gives you the normalized feature. Now that I have this, I basically have something in which I could do Euclidean distance to compute the closest vector. And we can start to have something that Talo has to play back those animations. So what I would do is that I will have a player, and basically what the player does, it stores the current frame I'm playing and stores the current position and orientations of every bones, and also of the root of my character. I don't bother with the rest. And so when you say go to the next frame, what it does, it basically here, you know, all my data in my database is moving in space. So what you have to do is compute the displacements. So say that if I want to play frame 10, I need to know how much it moved from frame 9 to frame 10. And that's the offsets I want to add to my character. So I want to compute how much displacement was inside of my animations and to add that to my character. So I can put my character anywhere I want, and I can let him follow the animation. So that's what this function does. Takes the actual animations, orientations of every bones, but compute the offsets of the displacements only. And we come back to this later also. So I import this. And now, if you want to play animations and map, the only thing you have to do is what I was doing before, taking my pad inputs and knowing what I want to do with my character. And then I compute the future trajectory. I compute the future position, velocity, and acceleration of my character. I do the same for my orientation. And then I compute the one in 10 frame in the future, 20 frame, and 30 frame is the future positions and orientation. And I get all basically the same trajectory I've computed before. What I'm doing is that I'm bringing back all that info into local space of my character, because, you know, right now my future positions and my future trajectories are in wall space somewhere where I want my character to be. But I want to compute everything relative to my character. All my data is relative to my character. So convert that relative to my character, and then I can build my query vector. So it's the same. It has the same size as the feature vector, so it's 33 dimension. And the easiest way and the most stable way to do it in this case is to start from the frame I played. So I take my feature normalized and I do a copy of the frame that was played. Why I'm doing this is because I'm using motion matching to play back animation. So I know that last frame I wanted to play that frame. So that means that I know the feet position, the feet velocities, that kind of stuff of what I wanted to do. That's the really important thing here. I know that I wanted to play this frame, no matter what happened, that's the frame I wanted to play. So I expect the character to be in that state. So I take the feature normalized as a starting point for my query vector. And then I just change the future trajectory positions and future trajectory direction. And I do normalize those values the same way. So I really use the same feature mean and feature standard deviation that was used to normalize the vector in the first place. And that gives me the query vector. Okay. Now that I have the query vector, I could just ask which is the frame of animation that minimize the error between my query vector and the vectors I have in my feature vector. And I will not use any acceleration libraries or algorithm. I just brute force the search because I have around 20,000 frames in this case. So I can brute force that fairly quickly. Because the only thing you really need to do is compute, as I said, an Euclidean distance. So I take my feature vectors minus my query vector, square it, and sum the square. I don't even need to do the square root. If I only keep the square distance, it's all fine also. And then I arc sort in that big array, so it will tell me which row has the lowest value, and that will give me the best frame. So I pick the best frame. That's the one I want to play. That's the one that has the smallest error. That's the best score, let's say. The only thing I would do is, and I would just always pick the best one. The first thing I'm doing is something that happens a lot when you're doing motion matching, that it might find that the best frame is the frame that was just right before you. And then you will start to loop and only play a really small piece of animation. So just to avoid that, going backward one frame, I just make sure that it doesn't pick any. I will go in the order of the one it shows and make sure that you don't pick any of the frames that were, in my case, less than 5 frames in the past. And that would be way enough for him to never go back in that weird loop. And the other part I'm doing is the opposite. I'm making sure that the frame it picks, it's not at the end of one of my animations. So I just ban him to pick anything from the frame range minus 30. So it cannot pick something that is 30 frames before the end of the animation. So basically the last second of the animation is gone. That's what I'm doing here all the time, because my takes are really big. So if I discard 1 second of each of those, it's not a big deal. And that gives you the best frame of animations. And so I can set to the system, now it's time to play that frames. And what I do is that I tell him to play the next frame. Why? It's because I don't have any delta time. I'm playing at 30 frames per second in my system here. So this feature, query vector, pick the best matching animation now. I need to play the animation, so I tell him, go play the next frame of the one you matched. And that's why if you have the query vector now, if I repicked the same feature, normalized, and nothing changed in my input, I have really high, nearly 100% chance that it would pick the correct frame. It will go back to the next frame, and so it will play the next frame. This one will repick the same frame. That one will go back and play the next frame, and so on and so on. So that's one of the ways to stabilize that kind of stuff. Also, just making sure that every frame it picks the next frame. There is also the way of saying that you don't want to play. Don't want to compute the search to the database every frame. You know, if your input hasn't changed, your trajectory was correctly computed. I mean, for a bunch of frames, you know that it will just say, play the next frame. You don't need to do that search every time. You could say, if the input doesn't change, recompute the search to the database every X frames. I haven't gone that far. I'm just recomputing every frame. So, and then we play the animations and we can see what happens. So, in idle, of course, I don't have any data for idle, so there you go, he goes nuts. But as soon as you go motions, you could see that they start to pick the animations it prefers. And we could see every time you pick the different animations right now, it pops, but it does map, you see, align the positions, the future positions. So the yellow is what I'm computing, and the black is the best animation is found to match my request. And it follows different orientations. If we want, you can switch and get a bunch of animations. Now, of course, it pops all the time. So the first thing that we want to do is to make sure that all that popping disappear and that we can have something smooth. And that's what I have here when I activate the inertialize. So inertializations is also an algorithm that has been quite popular lately. It's basically the way of saying that instead of trying to blend animations together, we will tell that we have a stream of motion, which is what we have here. And then every time we have a big discontinuity, so every time you pick the different animations, you compute the offsets, the amount of error that you have between the old animations, the old frame, and the new frame of animations. That give you an error. And then you will try to, you will add that error on top of your current frame, and then you will slowly damper down the amount of error correction you do. So basically, you have a discontinuity, you compute the offsets between the discontinuity and the old animations, and then you slow down, you slowly remove the amount of error you had between the two. The way the initializations work, it's what we have here. In this case, thanks to Daniel Holden again, and the way he developed the spring, we could use the spring to also reduce the error using a spring. So basically, you said how much error I have right now, and then I need in 0.2 seconds to reduce that error to 0. And using a spring, it would also take into account what was the velocities and angular velocity of your character. So you're making sure that if you had a motion that was doing this, it will keep the accelerations, and it will not just stop and go down. It will just keep that same motion, thanks to the fact that the damper will take into account the velocities of each bone. So that's why we had computed the actual bone velocities and bone angular velocities of our animation. It's to be plugged into the initialize. So if your character moves in one direction, it keeps the same motions and it started to blend without any abrupt change. And that's because the spring use, again, the position and velocities. So in this case, the positions becomes the amount of error between the two pose, and the velocities is the direction in which the bones was going. So was it going in the right direction to remove that error? Was it going the wrong directions to remove that error, and that kind of stuff? And that damper works properly to reduce the amount of error to zeros and keep the velocities. And so the initialize does this every time we have a discontinuity. So basically every time we don't play the next frame we're expecting, we compute the amount of error that led to, and then every frame we just let the spring remove the error slowly. And that gives us what we have here. Now, you could play with the velocities and how quickly you want to change the values and that kind of stuff. For instance, right now it's fairly the accelerations is kind of human when you accelerate, but it slowly stops. I can, for instance, change the half time when I'm releasing my pad, so it stops faster. So, that's a fast stop, but everything else is still the same. And finally, the last thing you could do when you talk about motion matching, but even in animation in general, is that I have the red is what I'm computing, what I want to compute, right? Is the velocities I computed through my simulation. And my character tries to follow that. What happened is at this point, you see I have a code versus animations, which is set to 0. Which means that the animation plays, and then when I finish playing the animations, I realign my simulations to where the character is. So right now it means that even if I ask the animation to do, well, if my simulations ask me to do something, the animation is not doing it, it's the animation that wins. You could have the exact opposite, which means that right now the red is what I'm computing with my spring, and the animations try to address that, and if it doesn't manage to match, it slides and come back to exactly, it realigns where my simulation is. And you could blend between the two worlds. In this case, I kind of match the velocities, accelerations, there, it slides here. But it kind of match what we want. For instance, if I accelerate too much, that does not exist inside of my database. You could see that my character is sliding like crazy, trying to catch up my simulation. And if I do the opposite, no matter what I'm asking the system, it only does what it found inside the animation. All right. So I could go back to the proper values. And you could do in between, for instance. Now, what we've done so far is building the database, building the feature vector, matching the feature vectors, but we've given the same importance to everything. I don't have foot IK, so I'm not locking the foot on the ground right now. I'm just playing animation, so sometimes it does slide when it blends because of the initializations, but kind of okay. So everything now matches with the same score. Everything has the same importance. All the feature vectors have the exact same importance. We might need or want to tweak a little what is more important inside of our feature vector. We might want to give more importance to some stuff. So what we need to do is that we need to weight the feature vector. Say all of my features might have a different weight. So what we'll need to do is that to multiply every of the values by the weights we want to associate them when we compute the Euclidean distance. But what we can do instead is realizing that if we have the weight here when we were computing the normalized feature vector, we can move our weights down here and divide our standard deviations by the weight. And if we do this, basically it means that now we have standard deviations that take into account the weighted importance we want to give to everything. And that means that nothing changed mathematically after. So if we just basically scale the standard deviations, the Euclidean distance, all the algorithm to do the search stays the same, except that now it takes into account the weights. So what I can do is this: I can have a weight saying that my hips velocity is important because I want to have some continuity inside of my motions. My feet position might not be that important, especially if I have a foot locking system. But the velocity is important, so I need to make sure that I don't pick animations that have the feet that doesn't go in the right positions. And I can give some importance to the future trajectories, but more importance to the future orientation. And I give it a discount factor for the features every time. And then what we have now is that I divide my standard deviations by the weights, and I renormalize. And if I do this now, all the weights are encoded in that one and encoded in that one, so I don't have to change anything here. I can keep playing, except that now it uses the weights, giving more importance to the future orientation than positions, giving more importance to feet velocities than feet positions, and you could play with those as you want. You get a bunch of different values. Now, that's in a nutshell exactly motion matching, at least when you want to do motion matching for locomotion. But there is another point that I want to talk, and that I will do in a different video, which is the link between what motion matching is compared to reinforcement learning. Really, in a nutshell, what we could see is that we have our current pose and trajectories and velocities and future trajectory. So this is Markov decision process. There is no difference from this process to anything else. And on top of this, if you've followed the reinforcement learning, the way I've discarded the future, discounted the future values should ring a bell on how Bellman equations and reinforcement learning works. It's exactly the same weights I've used here. That's what reinforcement learning would have done. So that would be for another video when we'll dig a little deeper between the relations with motion matching and reinforcement learning, and why I wasn't sure if I had to put this video inside of the reinforcement and learning series. But the next one will probably be. I hope you liked it, and see you next time.